Hello everybody, my name is Yukihiro Kishi. I'm from Tsunomiya University in Japan. Today, I'm going to talk about driving assistance for personal mobility using shared controller with semantic map. The route from home to the nearest bus stop or train station and from the station to the destination are often not covered by public transportation. These are commonly referred to as first and last miles. In recent years, personal mobility has attracted attention as a new mode of transportation for these segments. Personal mobility refers to single-user mobility devices. For example, in our laboratory, we have developed a joystick-driven mobility that allows the user to steer simply by tilting the joystick. However, as you can see, driving on narrow sidewalk is challenging. The user must avoid obstacles such as pedestrians while preventing deviation from the drivable sidewalk, which makes navigation difficult. Therefore, the purpose of this work is to realize safe driving assistance for personal mobility. In our previous work, we proposed a shared controller for driving assistance based on the artificial potential method. In this work, the artificial potential method is used as a motion planning based on attractive repulsive force model. First, the user's joystick input generates an attractive force towards the destination, while personal mobility equipped with a 3D LiDAR detects obstacle and generate repulsive forces. By the resultant force, the mobility can avoid obstacles and navigate to the destination. However, a mobility equipped only with a 3D LiDAR had difficulty recognizing the sidewalk. As a result, it could deviate from the sidewalk during obstacle avoidance. To address this issue, semantic segmentation is applied to RGB images, where pixels are classified as either drivable sidewalk or non-drivable areas. Furthermore, these are combined through sensor fusion of 3D LiDAR and the camera. Here, let us explain our sensor fusion. First, the sidewalk is classified using semantic segmentation on RGB images. Pixels corresponding to the sidewalks are colored reds, and pixels out the sidewalk are colored black. Since regions on the sidewalk occupied by obstacles are also non-drivable, we define the drivable areas as obstacle-free sidewalk, while obstacles on the sidewalk and regions outside the sidewalk are classified as non-drivable areas. Then, the segmentation images and 3D point clouds are combined through sensor fusion. As a result, each point is classified as either drivable or non-drivable. However, this classification is limited to the overlapping field of view of sensors. Moreover, point clouds are sparse near the mobility device and between point clouds, making recognition difficult. Therefore, our first approach is to build a semantic map via online SRAM, so that the mobility can recognize the sidewalk more robustly. Here, let us explain our semantic map. These classified point clouds obtained through sensor fusion are then used for online SRAM. Online SRAM accumulates 3D point cloud in real time to build a map. As a result, a semantics map is built. In this map, the area inside and to the right of the white line is classified sidewalk, while the area to the left is classified as non-drivable areas. Using this map, the mobility can recognize drivable areas and avoid obstacles on the sidewalk. However, Dynamic obstacles such as pedestrians are classified as non-drivable areas. As a result, their walking trajectory are accumulated and included as non-drivable areas in the map. This makes it difficult to drive on sidewalks that should normally be passable, as they appear blocked. To address this issue, pedestrians are detected via point clustering, and their corresponding point clouds are excluded from the online SLAM process. Here, let us explain excluding pedestrians from online SLAM. Using the classified point clouds, objects are detected by applying point cloud clustering. Pedestrian point clouds are detected by threshold of heights and widths. Next, online SLAM is performed using point clouds, excluding pedestrians. This allows the mobility to build a map M without pedestrian trajectories. The final map is obtained by associating the current pedestrian point clouds with M. Using this map, the mobility can recognize drivable, non-drivable areas and pedestrians. Therefore, the mobility can provide driving assistance through the shared controller based on this map. Here, let us explain the shared controller. Based on the semantic map and the user's directional inputs, the control commands are computed. First, the attractive potential generated by the user's joystick input is defined using the driving input D. When the joystick is tilted in the direction indicated by the red arrow, the potential field decreasing along that direction. Next, we use two repulsive potential for non-drivable areas and pedestrians. 1. The repulsive potential generated from the non-drivable areas. The closer mobility approaches non-drivable areas, the larger repulsive potential becomes. 2. The repulsive potential generated specifically for pedestrians. This repulsive potential increasing exponentially and smoothly with decreasing distance. Finally, the resultant potential is defined as the sum of these. Under the gradient of this resultant potential, the mobility can avoid non-drivable areas and pedestrians while navigating towards the destination. Here, let us explain the experimental setup. We conduct experiments a 3-meter wide road within the campus. Although the white lines are drawn, the area inside the right of the line is defined sidewalk. The area to the left is defined as another road. Pedestrians are placed as an obstacle. The personal mobility device is equipped with a joystick, a 3D LiDAR, and an RGB camera. The parameters set as follows: a threshold of 3 meters for non-drivable areas, 5 meters for pedestrians. In these environments, the user continuously tilts the joystick forward. 3 tries are conducted from start S to go G. Here, let us explain the experimental results. The mobility reaches the goal in all trials with driving assistance without collision or deviation. This figure shows navigation trajectory. Blue segments indicate area where the user input affects the motion, while green segments indicate areas influenced by repulsive potential and driving assistance. This video shows the first avoidance trial, where pedestrian approach the driving assistance act to steer left for pedestrian avoidance. Near the white line, the driving assistance act to steer right, preventing sidewalk deviation. Here, let us focus on the first trial. The blue circular area visualizes the resultant potential around the mobility. In this visualization, higher potential values are shown in white and lower value in blue. Therefore, the mobility is located at the center of the resultant potential. The pedestrian is represented by yellow point clouds. Let us examine this potential field. The user directional input generates a change in delta U, allowing the mobility to move straight towards the destination. When the pedestrian came within 5 meters, a repulsive potential was generated based on delta U. The mobility steered to the left to avoid the pedestrians. As a result, the mobility approached the bright line. However, a repulsive potential from non-drivable areas became large. Following delta U, the mobility steered right to return to the sidewalk and continue straight. Consequently, the mobility navigated towards the destination without deviation. This is the conclusion of this presentation. The purpose of this work was driving assistance for personal mobility. However, sidewalk recognition was difficult and pedestrian walking trajectory were included in the map. Towards this challenge, we built a semantic map via online SLAM and excluded pedestrians from the SLAM process. The mobility based on driving assistance using a shared controller successfully recognized pedestrian sidewalks and navigated towards the destination. That's it. Thank you very much for your kind attention.